this is the forces topic, otherwise known as dynamics. This is section 4.1. It's going to be an introduction to all the different types of forces. Now, what I am going to do in this section is, first of all, list all the different types of forces that I can think of. I'm going to break them up into categories. There's going to be contact forces, where the two objects have to be touching each other for the force to exist. There will be non-contact forces, where the two objects don't have to touch each other, but they're going to interact anyway. And I'm also going to have a very small little category with what I'm just going to call not new forces. These are phrases that involve the word force, but they're really ways of working with other forces that we've already described. So let's get started. The contact forces. Now, all right, let me back up just a moment. A force is defined as a push or a pull. And we'll talk about how each of these forces pushes or pulls on other objects. All right, so we'll start with the contact forces. Forces that are created only when objects are touching each other. So the first category is going to be contact forces. Now, for each force, I'm going to give you a symbol. It's always going to be a capital F with a subscript that is a lowercase letter. So you'll be getting the symbol for the force. And you'll also be getting a sentence or two describing that force very briefly. I want to list all these forces with those brief descriptions, and then go back later and go into more detail, and also supply little diagrams that show how these forces are applied in real life, real problems in the real world. All right, so we'll start with the list. All right, the first force I'd like to talk about is called the normal force. Okay, the normal force. Now, the normal force is going to be abbreviated, of course, capital F, little lowercase n. Now, just a quick mention, the unit for all forces, every force that I'm going to talk about in this section, all forces, is the Newton. The unit for all forces is the Newton. All right, now that's also a capital N. All right, but let's not confuse normal force with the unit Newton. All right? What the normal force is, when an object is resting on a surface, now that surface might be flat, that surface might be at an incline. All right, we'll talk about that in other topics in more detail. But the surface, to some extent, supports the object. Now, the surface might not be strong enough. The normal force might not be strong enough, and the object might break through the surface. But let's just look at the situation where the surface is strong enough to support the object. All right, the force is directed upward. It's the surface pushing up, supporting the object. That's the normal force. Now, our next contact force would be an applied force. An applied force, right, capital F, lowercase a, right? An applied force I would define as a person or an animal, possibly a machine, pushing or pulling on an object. If a horse pulls a cart, then the horse is putting an applied force on the cart. If two people are standing and one person pushes the other person, that would be an applied force. On a pool table, if you hit a pool ball and one pool ball knocks into another pool ball, again, an applied force. When the cue stick knocks into the pool ball, an applied force. So I would call an applied force when a person or an object, or an animal, or maybe a machine, pushes or pulls on another object. That's an applied force. Now, friction, the friction force. I'm going to describe 3 types of friction force. First of all, it's going to be F, capital F, lowercase f in general. And you can have static friction. You can have kinetic friction. And I'm going to also list a special type of friction that, again, could probably be either static or kinetic, but air resistance. Air resistance is a type of friction. We can list the abbreviations for static, kinetic, and air resistance as, for static friction, we'll list it as F, little f, S. Okay? For kinetic friction, the symbol would be F, little f, K. And for air resistance, let's just say F, AR. Now, your teacher might use slightly different symbols. A textbook might use slightly different symbols. But of course, your teacher will define the symbol. The textbook will define the symbol, and you use it. As long as everybody agrees, the symbols are not that important. The most important thing is that everybody agrees, so we know what the symbols mean when we start a problem. Now, friction would occur when 2 objects rub up against each other. The objects have to be touching for the friction to happen. Static friction occurs when the objects are not moving relative to each other. So take the example of a box on a carpet or just a floor, and you're trying to push that box to get it to start moving. The box is static, it's not moving relative to the floor, and you want to get it started. So you give a push, and as soon as it starts moving, that becomes kinetic friction. Kinetic friction is when you're moving the box across the floor. Between the bottom of the box and the floor, that's kinetic friction. Air resistance, let's say an object is falling through the sky. It's passing by, rubbing up against air molecules on the way down. So it's a type of friction, and we call it air resistance. Now, it could also be, for example, a car accelerating, and we know that the air resistance puts drag on the car. Right? So that air resistance could be something falling vertically or something moving horizontally, trying to go faster and faster, trying to pick up speed. All right? So those are the different types of friction forces that we're going to encounter. All right, I'm going to erase these, and we're going to put some more contact forces up here. All right, again, we want an overview. We want to list all the different types of forces that we're going to be talking about in this whole topic. Okay, tension. Tension. Tension is the force in a string, a wire, a cable. Tension can only pull. A string or a cable cannot push. They can only pull. So, for example, if you're walking your dog and the dog is pulling, there is tension, there is a tension force in that dog's leash. We'll call it a piece of rope. When you have a bridge and it's held up by cables, there is tension in the cables. Now, every string, every cable, every wire has a certain rating. If you hang something too heavy from that string or wire or cable, if you exceed the rating, the tension that string or wire or cable is manufactured to support, then that string or wire is going to break. All right? So tension is the force in a string, a wire, a cable, a rope. It can only pull. A string or a rope cannot push. Now, one thing to remember about tension is that all different strings, ropes, wires, and cables have a certain maximum tension that they can withstand. If you exceed that tension, the string or cable, etc., will break. For example, different strengths of fishing line are meant to pull in different weights of fish. Right? A very light fishing line can bring in a small fish, like a little herring, or maybe a small striper, a baby sea bass, a baby striped bass. But to get an adult striped bass, you would need a fishing line that has a much stronger tension rating. If you go over that tension rating, if you put something too heavy on the end of the string, rope, cable, wire, or fishing line, then that string, rope, cable, wire, or fishing line will break. All right, another contact force would be the buoyant force. The buoyant force applies to fluids such as liquids or gases. The buoyant force is what enables an object to float or rise in a liquid or in a gas. For example, if you were to put an object that floats into water, then the buoyant force could either equal or exceed the object's weight. And the object will either float in the water or the object will rise up into the water. If the buoyant force is not strong enough, the force of the water pushing upward is not strong enough, then the object will sink into the water if the weight of the object is greater than the buoyant force. This also occurs in gases such as air. For example, in a helium balloon, the buoyant force is greater than the weight of the helium balloon, so the helium balloon rises in the air. Another contact force would be the spring force. Now, keep in mind that there are two different types of springs, although all the calculations would be about the same. You have compression springs. These are springs that you push, and then the spring pushes outward when you release it. Or expansion springs. These are springs that you pull, and then the spring pulls back inward when you release it. I'm going to erase this again because I'll put all those forces together, forces that pertain to vehicles. You've got thrust and you've got lift. We'll do capital FTH for thrust. We'll do capital FL for lift. Now, you could also talk about drag. That's air resistance. We mentioned that earlier. Maybe you would put F capital D for that. Drag would be air resistance, dragging the car back, stopping the car from going as fast as you'd like it to go. All right, now, thrust. All right, when a rocket lifts up off the ground, the gases are pushing down. They're coming out the bottom. And the thrust is the force pushing up, back up on the rocket, making it go faster and faster up. Thrust could also be the engine in a car. In other words, the engine is providing a force. Now, it gets a little complicated, and you keep changing the direction of that force, but ultimately, it's causing rotation in the tires, and you've got a thrust force pushing that car forward. Lift is the force that causes a plane to go up into the sky. The plane has to be moving forward, and the wings and ailerons, the little flaps on the plane, have to be at a certain angle so that the lift is able to push upward on the wings and the body of the plane and push it up into the sky. All right, so that's pretty much all of our contact forces. All right, now what you're going to want to do is download the list of all the forces, right, or make a list as you're watching the video. Okay, since you can do that, I'm not going to put them all on the board at the same time. You can do that, or you can download the list from the website. Now, what about non-contact forces? Forces that push or pull objects, and yet the two objects involved are not touching. All right? Non-contact forces. And you say, well, how is it possible for one object to push or pull on another object and yet not touch that object? Well, you've got very, very common everyday examples of these non-contact forces. The first being the gravitational force. Gravitational force. The common name for the gravitational force is weight. It is also sometimes called force due to gravity. Right? It is the weight of the object. The symbol for gravitational force, capital F, lowercase g. Sometimes you'll see it as W for weight, but that's not a good symbol to use because we really want to use the symbol W for work, not for weight. So we prefer to use, look, gravitational force, right? Just like all the other forces, capital F and a lowercase symbol, subscript, all right, to distinguish the force from the other forces. Now, okay, I am standing on the Earth. Objects that have mass, like me and the Earth, attract each other. So the Earth is attracting me. It's pulling me down. And that is my weight. That's what my weight is. Now, I'll just mention that when you get on a scale, the scale is actually measuring your normal force. All right, but we'll get into that later. All right? My weight is a result of the Earth pulling me down. Now, even if I was 10 feet up above the Earth, not touching the Earth would still pull me down. If I was a mile up above the Earth would still pull me down. All right, so objects do not have to be touching for the gravitational force to pull them towards each other. Now, let's take the example of two of these expo markers in outer space. All right, I put them right about here, this far apart from each other in outer space. Over millions of years, the gravitational force of the two markers, they both have mass, attracting each other. The gravitational force, this one attracting this one, and this one attracting that one, they would pull each other together over millions of years and end up together. All right? And that's how planets are formed. Little particles of dust are attracted to each other. Little pebbles are floating in outer space are attracted to each other. It's called accretion. And these rocks, these particles come together. They get bigger and bigger and bigger. All right, because of the gravitational force. But again, let's just call the gravitational force your weight, the object's weight. I will also just mention briefly, keep in mind, the Earth is pulling me down and I am pulling the Earth up. But we'll get into that in a much, much more detail in a much later section. All right, the gravitational force. All right, the next contact force. All right, the electrostatic force. The electrostatic force. All right, I'm going to get rid of this. Electrostatic force. The symbol is going to be capital F, lowercase e. Now, the gravitational force occurs because two objects both have mass. The electrostatic force, sometimes, we'll just call it the electrostatic force. The electrostatic force occurs when two objects have charge. You know that two protons, two positives, are going to repel each other. They're going to push each other away. So a positive and a positive will push each other away. You know that a positive and a negative, right, proton big, electron small, okay, will attract toward each other. So this electrostatic force can be a pulling force or a pushing force. They can attract objects together or push objects apart. Right, electrostatic force. Let's get some more non-contact forces. All right, again, these are when objects do not have to touch each other for the forces to occur. All right, the magnetic force. Magnetic force. We're also going to use capital B for the magnetic force. Now, I understand that could be the buoyant force. You have to be clear in a problem. If there was ever a problem with a magnetic force and a buoyant force in the same problem, you would have to distinguish one of them somehow with a different letter. All right, but in any case, the magnetic force, all right, occurs when two magnets, all right, a north pole, each magnet having a north and a south pole, all right. If you have, for example, the north pole of one magnet close to the south pole of another magnet, north-south opposites are going to attract. All right, so they're going to pull towards each other. They're going to pull each other together. If you have a north and a north pole of two magnets, they're going to push each other apart. A south and a south pole would also push each other apart. Remember, a force is going to push or pull. One object is going to push or pull another object. Right, so the magnetic force is another non-contact force. Okay, the strong nuclear force. I haven't seen a simple, straightforward symbol for strong nuclear force. For lack of a better symbol, I'm just going to put capital F, strong nuclear. Okay, capital F, strong nuclear. That's that's going to be the symbol. All right, now, the strong nuclear force is what holds protons together in the nuclei of atoms. It can hold protons together, and it also holds the neutrons together. So in any atom of deuterium, that's a proton and a neutron. That's the hydrogen atom of a proton and a neutron. In any atom of deuterium or larger, the strong nuclear force is holding the nucleus together. What do the protons want to do? It's positive, positive. They want to explode. They want to repel each other. They want to fly apart. If it were not for the strong nuclear force, all the nuclei, all my nucleuses, all right, all the nucleuses and all the, right here, all right, would all explode. The protons want to repel each other. The strong nuclear force is stronger than the electrostatic force the protons wanting to push each other apart because of their positive charges. The strong nuclear force is stronger than the electrostatic force. It pulls the protons together, and it also attracts the neutrons together. Now, the reason that both protons and neutrons are affected by the strong nuclear force is because the strong nuclear force holds quarks together. So the strong nuclear force holds quarks together, and since protons and neutrons are both made out of quarks, the strong nuclear force holds protons to protons, protons to neutrons, and neutrons to neutrons. It holds all nuclei together that are a proton and a neutron or larger. All right, the last force that I'd just like to mention, we don't talk about it very much, but I will mention it, is the electroweak force. The electroweak force. And the electroweak force, we'll just put capital F, EW, I just made that up, all right? The electroweak force is a force that is involved in radioactive decay, among other things. All right, again, we don't talk about that force a lot. Now, I did make a little error earlier, and I said that the electrostatic force was a contact force. You know, of course, it is a non-contact force. We were discussing the electrostatic force during the during the list of non-contact forces. So non-contact forces, we had the gravitational force, the electrostatic force, the magnetic force, the strong nuclear force, and the electroweak force. All right, now, I'd like to talk about two more forces, but they're not new forces. So I'm just going to call this little section not new forces. Not new forces. These are ways to apply and utilize our knowledge of other forces that we've already discussed. So, the first not new force that I'd like to talk about would be the centripetal force. Centripetal force. Now, there is an old term called centrifugal. It's wrong. It doesn't exist. It never did. Right? It's a mistake. If you see it, ignore it and maybe don't continue reading that source because somebody doesn't know what they're talking about. Okay? So if you see the word centrifugal, run. Okay? It is centripetal force. The symbol is capital F, lowercase c. And the centripetal force is another force that is acting centripetally. It is causing an object to move in a circle. So you could have, for example, tension acting as a centripetal force. You could have the gravitational force acting as a centripetal force. You could have static friction acting as a centripetal force. Again, a centripetal force is a force that is causing an object to move in a circle. So, tension. Put a rock on the end of a string, swing it around, and the tension is causing that rock to move around your head in a circle. Gravitational force. If I'm the sun, I'm applying a gravitational force to the earth. I'm causing the earth to move, not in a circle. An orbit would be more of an ellipse. But I am causing the earth to move around me. And when we do problems To simplify the problem, instead of using an ellipse, we're going to use a circle as an orbit to simplify the math. All right, so the gravitational force, the body in the center, is pulling on the body that is orbiting around it, and that gravitational force acting as a centripetal force is causing that body to move around the other body, the central body. Static friction, acting as a centripetal force when a car is making a turn. The car is moving in a portion of a circle. It's static friction pulling toward the center of the circle. All right, when we get to a later section, we'll explain why it's static friction, not kinetic friction, that is keeping the car on the road. Okay? But again, a centripetal force is another force that we already studied that is acting centripetally, causing an object to move in a circle, an ellipse, causing an object to move around another object. All right, so centripetal force. The other force, the phrase that has force in it that you're going to hear, that is not a new force, is the phrase net force. All right, so a net force. A net force simply means you are adding up the other forces. So again, we already talked about all the other forces. First of all, it's net force, and the symbol would be capital F, lowercase net, all right, net, net force, and you are simply adding up other forces. All right, for example, if I am pushing an object with a force of 50, all right, newtons, all right, my F applied is 50 newtons in that direction. The object is moving, all right. Let's say the object is going, I'm pushing it and it's going faster and faster, all right. So the friction, all right, the friction, let's say, is 20 newtons. FF, all right, FF kinetic is 20 newtons. It's going to be actually negative 20. All right, well, yeah, all right, negative 20. Okay, the net force is 50 minus 20. The net force is 30 newtons. We took these two forces, we added them together. All right, one's going this way, one's going that way. So adding them together means 50 plus a negative 20, and F net, the net force, is 30 newtons. Okay? So net force is not a new force, it's just adding up other forces that we already know about. All right, and I'm gonna leave that. I could go into detail about net force for an hour. Not gonna do that. Okay? The objective of this section, and we're going to stop it right here, was to list all the contact forces, all the non-contact forces, and the two phrases, centripetal force and net force, that describe other forces, working with other forces in particular ways. So we've got the list. Now, what you're going to find in the next section is a detailed definition of each of these forces that we've listed, and a diagram of each of these forces in a real world problem, a real world situation. All right, so that's what is going to happen in the next section, and I will see you in the next section.